Are
we on?
That's okay. Hello, thanks everyone for showing up. I was going to smile for Andy's photo first, and then we'll continue.
Nice.
Hi, so I don't know how many of you are familiar with what we do, but we're Ziva. So we're a Vancouver-based software company, and we were started by people that are really passionate about making software which can make the best characters and creatures. So as a team, we're only a 4-year-old company, but the experience in the team is, I think we sort of added it up. It's about 200 years of experience. So what we're going to show today is we're going to start with a demonstration of Ziva VFX, and that's our current commercial product. And what that is it's a Maya plugin that allows you to do finite element simulation for characters and creatures. And then following, by the end of the workshop, I'm just going to give a sneak peek of some tools which we're going to be releasing in the near future. With that, I'll just hand it over to Andy because we're kind of short on time.
Yeah, we didn't want to go through a reel.
Yeah, why don't we play a reel? We'll play a reel first.
Some stuff. Some of it is...
There we go. Yeah. So this is an example of a character simulation that we've built in-house. So when we started the company, we did an early beta with a whole bunch of visual effects companies, and we were brought out of beta early because Sony Pictures Imageworks wanted to use the software for Suicide Squad and Ghostbusters. But this is some internal stuff that we've done internally in order to stress test the software. So as a team, we have a bunch of highly skilled developers, but we're also cross-disciplinary, where we have a bunch of internal TDs. So we'll make our own content in order to stress test the software and make sure that we encounter the problems before our customers do. And this is a really good example of doing that, because it sort of tested the full scope of what's required in order to create something that looks, film quality internally. So this is just sort of an overview of some of the functionality. You'll see more of that as Andy goes into it again. And then this here is trying to illustrate the difference between, if you look at it a couple times, you'll see the difference. But the one on screen right is a line that's been skin clustered. So there's nothing fancy going on there, but it's a skin cluster. The one on screen left is an anatomical simulation. So we've built a single anatomical model, like the same one that you saw earlier doing a walk and doing a run, and we've just given it new animation, and it's running up the tree or cylinder or whatever this is. And these are some of the films that has used our software so far. So over the past year especially, we've really had a big upswing in studios that have been adopting the software as the way to do things. Some stuff from the Meg. So the Meg was a big production that used this past summer that was using our software to do all the sharks. So there are 2 primary vendors that were doing shots on the film, or there are 3 vendors. There was Scanline was leading it out of their Vancouver office, and then there was Sony Pictures Imageworks, and DNEG did a couple shots as well. And Scanline and Imageworks were responsible for the sharks, and they did that with our software. DNEG used it on Pacific Rim 2. And this is a smaller studio based in Sweden, Fable Effects, and they've been using it for a number of things. And this is a commercial that got nominated recently for, it was like an Ice Capades thing in the UK. And one of the cool things that this demonstrates is that even though we're building our software for the hardest case, which is anatomical simulation, in this case they had a traditional rig underneath, and they just sort of stuck a single tissue object on it to make it jiggly and sort of act as mesh relaxer. Macavision here in Stuttgart did this pig, and we were really amazed by the results, especially because they never once reached out for support. They bought some licenses, we didn't hear anything, and then this commercial dropped, and we're like, holy crap. So that was great. That's Suicide Squad. So the last 15 minutes of the Enchantress, her body was replaced and simulated with our software. This is One of Us, which is a company in the UK. And they're trying to specialize, or are specializing in creature work. This is a company, WeFX in Taiwan. So they used they started with the lion. So we have like some assets which are available on our store as well. And we sort of are trying to seed the community with good examples so that people understand, the approach to doing things, because it's a bit different than what you might used to. Like, traditional rigging, you go in there and you try to figure out how to subvert the software to make it, bend it to your will. But with what we're doing, we're trying to use a physical basis to do it. So rather than think of trying to cheat with the software, you want to think of how would you do it in the real world? Like if you were making a puppet out of meat, or whatever that is there. Maybe that was an unfortunate choice of word. Like, how would you do it? And that's sort of what that represents. This is some student work, which is pretty awesome, actually. And here's a gorilla that just dropped not that long ago. And we were really impressed by the results here. The person went straight through to doing a coupled skin simulation, so he's getting higher frequency wrinkles and stuff happening, which is neat. And that's it for the reel. So at this point, I'll hand it over to Andy to give an overview, sort of a demonstration of the software. And time will be a bit tight, so he'll probably go through it at a lightning pace.
All right. Let's flip the scene. Cool, just make that cool. Okay, hi everyone, my name's Andy. I'm a Senior Technical Director at Ziva. And as James said, I'm going to do a 101 type demo today on how to build characters and things with Ziva. So just wondering, like, how many people have heard of us before today? So there's been a couple. Okay, that's cool. All right, so I'll start in this scene and just kind of build out some muscles here. And then I'm going to move into maybe showing some skin stuff and some varying material properties as well, depending on time. And then James is going to show a sneak peek on something to do with the future at the end. So that's going to really be the exciting bit. Okay, so in the scene I've got some animated geometry here. So usually when you're authoring a Ziva character, you'll have some sort of animation in your scene to kind of run your sims against, so you can sort of get a feel for how the settings are behaving. So if I just hide the brachialis for a start, I'll grab the bicep object here, and I'm going to turn it into a Ziva tissue object. So with this selected on the Ziva menu here, currently we're a plugin for Maya, so when you load the plugin, you get these three menus. The Ziva transfer menu is new in Ziva 1.6, and we'll talk about that later on. But this menu here is generally to do with authoring. So if I was to come down to add simulation component here and choose tissue, you'll see that we get some new stuff in the scene. So I'm just going to hide a couple of these other objects so we can focus on this area. And so if I was to play this back now, you're going to see this object drop in space like that. So you can see we got some new stuff in the scene. So this solver node here, this is sort of akin to the nucleus node in Encloth. It describes some general things about the system. And we also got this tetrahedral lattice here. So this is kind of key to the core of what we're doing at Ziva with tissue. So this is called a tet mesh. It's made up of tetrahedra, and the tetrahedron is the simplest sort of 3D primitive you can have. And so we run something called finite element method, or FEM. And so all the physics and things are computed at this level. And the cool thing about FEM is that it understands volume conservation and real-world physics and things like that. So, yeah, I'll just carry on building some stuff, and hopefully you'll get a feel for how all this stuff works. So these objects here, I'm going to convert to Ziva bone objects. So under the Ziva menu, I can come down to add simulation component bone, and you'll see that we got some draw stuff here. So when I move this around, you're going to see these things follow along. You notice that the tissue didn't update because it's a physical solve. It's dependent on the frame before, so you can't jump randomly in the timeline. It's a simulation. So yeah, our bones are kinematic objects, which means you can drive them. It means they're non-dynamic for a start, but it means you can drive them with deformers or moving transforms around as a valid way to drive Ziva bones. And so now what I want to do is attach the tissue to the Ziva bone. So I'm going to grab some vertices that represent the origin and insertion of the bones or the muscles, and then I'm going to make an attachment here. So with the target object selected, I can come down to add simulation component attachment, and then I'll do the same at the other end. Shift select the bone, oops. And then You'll see that for every vertex that I had selected, it's looked up the closest point on surface on the target object. Another thing to note is that my tissue object is just an arbitrary geometric object, so we don't force people to use any kind of muscle primitive or anything like that. So it's really any piece of geometry can be turned into a dynamic Ziva tissue object. There's a couple of rules around triangles and things like that, but for the most part, you can use anything. Cool, so if I play this back now, it's just the tissue's gonna kind of follow along with the bones. And you'll see that while we do have some nice kind of dynamic effects and things, it's not really performing as you would expect a bicep to perform. So we can sort of keep adding things to the system and try and get the right performance out of the muscle, but this is a good place to start. So what I'll do next is add a muscle fiber to this. So as I'm sure you guys know, muscles are packed with fibers that get excited and they allow you to do work and things. So we have that represented in Ziva as well. So I'll change the material now so we can see it a bit easier. And then I'll make a fiber here. And then you can see that Ziva's tried to guess at the fiber field direction. So it usually does a pretty good job. And so if I look in the channel box while I'm authoring this stuff, you'll see that there's a whole bunch of nodes here that start with the letter Z. These are all Ziva-specific nodes. So every tissue object has a tissue node. Which describes some things about the tissue. You can change the material model. You can turn collisions off and on, things like that. It has a material node. This describes things like how stiff the tissue is, how hard it tries to conserve volume, density, that sort of thing. And you'll see here that we also have our fiber, which I just made a second ago. So there's an attribute on here called excitation, which takes a float between 0 and 1. So if I scrub this, you can see that it changes color. So yellow being fully contracted. And this is also keyframeable as well. So just to show that in action, I'll go to a frame a bit further down, say here. And then add another keyframe. And then I'm also going to add a cache to this sim so I can scrub the timeline later. So under the Ziva menu, I can come down to add simulation, cache, just add. And now when I play this back, you're going to see that the fiber is going to contract down the line. So the cool thing about this is that because Ziva's structurally aware and we conserve volume kind of by default, you can see when the fiber's contracting the muscle, it's also, so as it gets shorter, it's also squishing it outwards, which gives you these cool kind of volume conservation properties straight out of the box. It's kind of worth repeating that because it is quite a cool feature that you get this stuff for free with our simulations. So while that is cool to be able to keyframe this stuff, it's probably going to be quite tedious or laborious to hand key every time the bicep contracts, right? So we can actually delete that keyframe, and I'm going to choose to fire or excite the muscle with something called line of action, which is just a 2-point NURBS curve. So with this selected, I can use one of the Ziva tools to just help us make that curve. So I can create a line of action curve. You see I have it here. And I'm just going to move the endpoints around so it makes it a bit more obvious. And now I want to attach the endpoints of this curve to the bone. So prior to Ziva 1.6, you'd have to use some kind of rivet setup, but now we have our own internal one. So with this selected, the CV selected, and a bone object selected, I can come down to Ziva and choose rivet to bone, and then I can do the same at the other end. And now that curve is going to follow along, which is great. And now I'm going to connect that curve to the tissue. And the mechanism we use to compute how much firing needs to happen is called line of action or muscle line of action. So with those two objects selected and I choose muscle line of action, you'll see that we get this line of action node here now. So you can choose to fire the muscles based on position here. So this is position of the endpoints. If velocity or acceleration. I'm just going to stick with position now, but I'm going to make it 4 times more sensitive. So change that to 4. And then clear the cache. And hopefully now we'll see the muscle firing happen when there's actually a few more frames to this sim. So you can see it sort of changing color when the elbow bends. It's forcing the muscle to contract. Cool. So another thing that's worth mentioning, I think, is that you can change the resolution of the TET mesh on the fly. So you can only deform the embedded mesh, with as much TETs as you have. So these represent your degrees of freedom. So the more resolution you have, the higher amounts of curvature you can represent. So if we look in our node stack here in the channel box, you see there's a Z-TET node, and this has a TET size attribute, which we can change on the fly. If I could make that 4, and now we have a high resolution TET mesh. And it's kind of worth appreciating that it's quite cool that I didn't have to change anything else about the system in order to adjust the simulation mesh. And other systems don't do that. They're kind of bound to the actual geometry, whereas ours is decoupled, if you like. So if I play this back now, you're going to see a little bit more curvature in there. So the only downside you can't go too crazy with adding TETs to your scene, because it's basically the more TETs you have, the slower your solve's going to be. So you're trying to find some kind of balance between the deformation that you're looking to represent in your solves and the amount of TETs in your scene. So just worth mentioning that. Cool. So the next thing I'm going to do is add another muscle. So add the brachialis. And then just to sort of illustrate how quick it is to bash through this stuff, you can sort of just add the tissue, do the origins and insertions. Attachment. And then I'm going to make a fiber on that. Oops. Add some fiber. And I'm going to use that same curve to drive it. So line of action. So we have a second line of action node now. I'm going to make it 4 times more sensitive. And now now that muscle's also in the system. So it's doing its thing. So we have another attachment type, a sliding attachment type. So with this sim, you can see that the bicep is really pulling away from the brachialis, which is obviously not what you would expect to see. So we can add a sliding attachment between the humerus and between the dynamic objects as well. So in order to do the vertex selection, we have a tool to help us do that. So if I just want the vertices that are kind of adjacent between the two surfaces, we can do that. So in the Ziva Tools menu, there's proximity tools. And I'm going to keep this radius at default and hit select. And you can see now that it's picked the vertices that are only within that radius. And we can shift select our target object and make another attachment. And this time I'm going to change its type from fixed to sliding. And I'm going to make it 100 times weaker. So these two attributes here end up multiplying to give you the final result. This is short for exponent or exponential. So it just means it's kind of a convenience measure, so you don't need to maintain a bunch of zeros and attributes. And then I'll attach these two objects here together using the same methods. Sliding. And then play that back now. And you're going to see these two objects are going to feel like they're more part of a complete system rather than acting independently. That said, though, they will preserve their own independent motion because they can, slide on each other. So that's kind of a cool thing. Right. So that's sort of the super basics of building anatomical muscles. I guess the rest of the process really is adding more muscles as you go and building up the system and trying to run it on different animations and check the performance and things. So I can probably go on to doing some materiality stuff and maybe some skin stuff before the 1.6. I'm kind of bashing through it because we've got time constraints. So I'll just jump into a skin scene now.
Yeah, and just so everyone knows, I think all this material is covered in our videos on our website. So
That's true.
if any of this is unclear, if you don't see us directly, you can see it there. Both Andy and I are also, and Lonnie are quite active on the forum. And Andy, I think, has the record for the most responses, though. So.
Yep. Cool. So I've just got a subset of the skin here so that we can get sort of a nicer frame rate for a live demo. So what I'm going to do is just go through how you would build skin for this area, and you'll be able to extrapolate out that it's the same process for a full skin. But I'll just show this image first. This is kind of the pipeline that you would use to make a character. So this part of the pipeline here is the animation side. This is what you would give to an animator. There would be no Ziva nodes, no Ziva setup at this stage in this rig. So it would be real time. It would have a basic skin cluster on it, and it would also be responsible for moving the skeleton geometry around. Then you would bake out your skeleton geometry and then import it into your muscles rig and use that to drive your muscles. And then you would bake out the muscles and use those to drive the skin in conjunction with the skeleton. And then you'd blend it back to your original skin cluster at the end. So in the skin thing that I'm about to show, we're at this point here. So we have the cached muscles in here as well, but these are now converted to Ziva bone objects. So you can see there's some animation on here. And what I'm going to do is create a dynamic object out of this mesh, which you can see has thickness. So you can see it's actually made up of 2 layers. So the inner layer, I think I have the build layers here, represents kind of the contours of the muscles and bones underneath. I actually used our cloth solver to help model this. If we have time, I can show that, but maybe not. And then you have an outer layer, and I've just built a border between these two. So then what you have is you combine it all, merge the vertices, conform the normals, and you end up with a closed volume that you can run collisions and things against. So I can convert this to a Ziva tissue object now, add simulation component tissue. I'm going to change the tet size to something like 4. And then I'm going to attach the ends. I'm going to attach all the borders to the underlying bones. And to do that, I'm going to use one of my scripts, because I don't want to manually make all the attachments, because that'd be boring. So I can do a vertex selection. So I can use our proximity tool to do the vertex selection. So I need the tissue first. Then I'm going to use all the vertices that are adjacent to or concurrent to the border. Ziva tools, select vertices. I'll make this really low because they're on top of each other. I'm going to store that selection. And then basically I'm going to use something that's going to allow me to look up the closest point on everything and make the attachments that way. Cool. So now if I grab some of these bones, you can see that it's made attachments in there. I've got an extra one here now. Probably don't need that. So this is another thing I can show, that a lot of the maps in Ziva are paintable. So if I wanted to change this attachment after I'd made it, you can see there's actually a grayscale map. So I don't want that attachment on that vertex there, so I can just replace it by painting it off to 0. And so this is really common in Ziva. Many things are paintable like this, and you can alter them after the fact, which is quite cool. It's also the means by which we're able to transfer setups from one character to another, which we'll look at later. Cool. And then I think I have collisions on. So the idea is that collisions and things of the underlying objects keep the mesh from going through the underlying objects, and then you get this skin simulation. So this is the first look, and then we'll add another thing after this to make it better. Already have it's holding up pretty well. One thing that's happening in here is that we're sort of losing the silhouette a little bit. And in fast motions, actually the skin's going to come off the underlying objects, because if there's a lot of inertia in there, there's nothing keeping the skin onto the muscles and the bones. So we have this concept of, we used to run something called a fascia, which was kind of a cloth sim that would keep everything on, but now we can do that stuff at the tissue level. So if I'm going to do that trick to select vertices again, so I'll select the skin tissue, then that inner layer, and then you select vertices, and then I'm just going to make a material. So we can have a material layer here, and then if I select the skin tissue, you see now we have two materials. Now material layers kind of function similar to layers in Photoshop, in which the layer on top takes precedence. And then the way to reveal the materiality of the stuff underneath is to paint an alpha map, or in this case, a weight map. So I can come in here, and it's already, because I had those vertices selected, it's already painted that for me. So you can see that's painted there. There's that again. Probably paint that off. Cool. So now I can use that material. You'll see that we have this pressure attribute in here. So this is going to put a force in the normal direction, and just going to effectively project the tissue down onto these underlying objects. So I could change this to, I think it's negative. I'll make it 1200 or something. And then we have the surface tension attribute as well, which is going to shrink the tets in the orthogonal direction to the normal of the surface. So it's going to kind of like shrink them anisotropically. That's right, isn't it?
Yeah, it reduces the surface area of the surface triangles.
Yeah.
Yep.
And then, so I'll make that 20 or something. And we want to ramp those attributes on over time. So we can do that here. Because if you have it just jump on the first frame, it's going to be too fast for the solver to catch, so it'll jump through the underlying stuff. And you'll miss some collisions. Do 10 frames there. Cool. So all these green draw points here are collision proxy pairs. So that's where Ziva's telling you, okay, we've got an intersection here that we need to resolve. And so that's the collision pushing it back out. So we're starting to get some sort of intersection here. There's an attribute on the tissue node called contact stiffness. So this is how hard Ziva's going to try and resolve or how much energy it's going to use to resolve the intersection. So I could change this to 10 to the 7. And I'm going to do that on all the bones as well. So I could do type Z-bone, and then I get all of those, and I can make this 10 to the 8 as well. And hopefully that'll clear up some of those intersections. So this is really kind of a new way of approaching skin, I would say. This is very different to the traditional methods. It's going to give you a lot of extra cool stuff for free. It's going to help you redistribute the points properly. It's going to give you sliding. You're going to see shape change and inertia, secondary motion, all that stuff should come out of the solve. So that's kind of the really basic approach to doing skin with Ziva, or fat as well. So how are we doing for time? Should I jump into some warping? Or?
Sure, yeah.
Cool. So, FMX. So one issue that we've addressed in Ziva 1.6 is the idea of scalability. So the idea that you can take all the hard work you've done on one character and copy it or propagate it out to many similar characters. So in this scene, I have 2 meshes. So the proportions of these 2 characters are really different, and that's by design, so we can show how robust the new warping tools are in Ziva 1.6. So this character here was actually one I downloaded from the internet, and I projected the skin of Mr. Ink. This is a free character you can download from our website. And I projected the skin from this character onto the mesh of the other one. And so that gave me 2 meshes with vertex correspondence or topology, matching topology. So I could make a blend shape between these 2 meshes if I wanted to. And I'm going to use them to warp the anatomy of the first character into the shape of the second character. So first thing I'll start with is warping some of the bones. So I'm actually just going to warp 2 bones just to illustrate how the process works. And I'll add these on a layer, because they'll come back. Cool. So in order to do the warp, you need to have the source object selected first, then the target, then everything you want to warp. And then in the Ziva transfer menu, you have some warping options. I'm going to select bone warp for this. I'm going to use the option box. I'm going to change the tet size to be 2. So what happens is actually a tet mesh gets generated on each of your surfaces, and then a harmonic function is solved between those in order to warp this stuff across. The bone warp is slightly different, and I can talk about why it's different in a second. If I hit warp now, just wait a second, and it's done. So I can bring back this stuff, and you can see now that the bones fit the shape of the target character, which is pretty cool. We got this Z warp display node, so we can actually change the bone warp after we've made it. So if I select this bone now, you can see that there's a couple of transforms at either end. So Ziva's tried to guess the kind of the extremities of your bone, and it's really good for things like the humerus, because it can keep the bone straight. Often if you use other warping tools or even the harmonic warp or an RBF warp, you'll end up with bent bones and things, which is not that ideal for especially this type of bone. So we can still alter this after we've warped it. We can add more landmarks. So to landmarks, bring up the tools. And if I paint a white vertex here, you'll see the warp actually jump as I add in more landmarks.
Yeah, the other thing to know with the way the landmarks are generated, when you paint an island, like so if you painted a splotch which included 10 vertices, the landmark will be centered in the center of all those points. So that's useful, like say at the head of a bone, if you want the landmark to be right in the middle of the head, you'd paint the entire head of the bone. It will put one landmark in the middle of it.
And then it's also quite noticeable the effect of adding in landmarks on the scapula, which has many different kind of extremities where it's not so obvious. So you can paint them in here, and it's going to be more information for the warper to work with. So the idea really is that you get your bones into a state that you're happy with, and then you use the skin and the bones to warp the muscles. So I have that prepared, ready. So we have these 2 meshes. I'm going to add these to this layer as well. And if I go into wireframe here, you'll see that this single object is actually combined. I've combined the skin and the bones together to create a combined mesh, and I've done the same on the source mesh as well. So we'll do the same thing again. And selected. So I'll select the source mesh, the target mesh, and everything I want to warp. And then in the Ziva transfer menu, I'll come down to this time. I'm going to use harmonic warp. And then the tet size is already 2. I'll hit warp. And then wait for a second or 2, and it's done. So it's really, really fast now to kind of get the anatomy of one character onto a similar character, it's actually really powerful. And it definitely addressed a lot of concerns for our customers and places that wanted to build out characters at scale. So this gives you a really, really good place to start from. In this case, I have some results where I didn't clean up the warp at all, so you can see what it looks like kind of out of the box. I'll just show the skin again. Bring this stuff back so you can see how close it is. So that's pretty cool. So once you have your anatomy geometry in place, then you want to copy all the Ziva stuff across. So we can do that right now. I could have a demo of that, which is builder. So I'm just going to work on a subset of the character so it's nice and fast for the live demo. So we just have an arm here and some bones and a solver. So if I want to copy the entire setup, everything to do with this solver, I just have it selected, and then in the Ziva transfer menu, come down to Ziva rig, I'm going to save it. And I'm just going to send it to a temp directory. Call it out.zbuilder, hit save. And then wait a little bit. I should add this. If you have the script editor open, you can see what it's actually doing. Those commands are actually sort of wrappers on top of a Python toolkit that we ship. So it's sort of a bunch of Python commands that allow you to store data and augment it and read it and things like that. It's really useful. So with that written, I can go to the corresponding geometry on the alien. And you can see that there's some animation on here, but there's no Ziva stuff on this geometry. So in order to do that, it works off names, so I can just load it straight in. Ziva rig load. You have the option, if you had a solver in the scene, you could add it to the existing solver, but in this case we don't, so we make a new one. And then go back to that temp directory. Wait a little bit, and again in the script editor, it told you everything that it was building, which is quite cool. And then you can immediately start iterating on it. So all that stuff's there. So again, it gives you a really, really good starting point to finalize this character. And in some cases, you may not need to make any adjustments at all, which is pretty powerful, I think. So I have a results scene somewhere. It's really heavy for some reason. So this is all the layers, so we've warped the skin as well on this one, and it's playing back the bake kind of slowly, but hopefully you'll get an idea. Tumble around. It's pretty cool. All the, that secondary stuff and the bicep and things is there as well, just to show. And then, you get skin sliding on the back. And it's everything that was in your source character is propagated to the target character. It's pretty cool. So I think from here we could do your thing.
Sure.
Last thing you want to show, and then
yeah, and then we can take questions after. So,
yeah.
If we could switch computers. Yeah. Press switch button. Yeah. Okay, cool. So. When we started the company, there was some key things that we wanted to sort of cover. So we wanted to, knowing how challenging the character space is, and the real goal for what we were doing is we wanted to make super realistic interactive characters. That's like the ultimate goal for the company, because ultimately everything's going to be super interactive and it's going to look completely photoreal. But we need to build that path that leads us to there. So when we started the company, we knew that accuracy was important for us. And Ziva VFX, what Andy was demonstrating there, represents the accuracy portion of what we're doing. So whenever we have a decision as far as how we're implementing things, we err on the side of accuracy over anything else. Though, we do try to make it really fast as well, but the focus of that product really is accuracy. We also, in the first year, we did some tests in order to just test out the whole theory of what we wanted to do. The anatomy transfer tools that Andy just showed is another one of those sort of key pillars that we're defining, because if you make one thing really well, it may take a lot of time and effort, but you want to be able to amortize that effort and then apply it to all your other characters. So that represents that. And then the third bit of what we were talking about initially was scalability and speed. So we did a machine-learned thing which trains off of the offline solver and then gives you a realistic interactive character. That's not productized yet. But what I am going to show first is this challenge that we've had around inputs to what we're doing. So we're running finite element simulation. So we're really at the mercy of the quality of the input data that we're receiving. So we wanted to start to consider solving that problem. And then there's some additional problems that we've also encountered that we felt that we could solve inside of this compute framework, which we call ZOA. So what the problems that ZOAs are trying to solve are those around speed, scalability, and then also being able to implement something in one place and then be able to view it in any other place. So for instance here, this is a zombie character that you can get from Sony Pictures ImageWorks, and we've been consulting with them over some of this stuff. But if I hit play here, you can see it's doing its thing, and it works visually. It's sort of what you'd expect from like a puppet. With rivets for the buttons and all that sort of stuff. But the main difference here that you won't necessarily know just by looking at it like that, but if I were to go here and look at the, I'm going to go old school hypergraph. There's nothing in the graph. Like these are just the controls, and these are the buttons and the mesh. And that's the whole thing. Whereas normally you'd expect it to be joint hierarchies, all this sort of stuff. All that's actually contained inside of the single node. So that's the ZOA player. So the idea there is you can be able to have have the exact same functionality of what you're used to doing in Maya, but now you're not limited to having this puppet live in Maya. You could have the same puppet run in Unreal Engine or in 3D Studio Max, or whichever applications we end up building players for. And I'll give you a sneak peek at sort of the authoring experience. This is all like early days from the UI standpoint, but this will evolve really quickly now that the underlying API has come quite a ways. So this just sort of shows you, authoring what you might see, like the nodes that might exist in your standalone thing. So like in this case, we're importing an FBX, and that has our skinning weights and our joint hierarchies and our meshes. And then we end up building our IK and our FK and apply the skin cluster and do all that sort of stuff. And then this graph here then is executed live inside of that ZOA player inside of Maya. Or eventually, you'll be able to run it in standalone standpoint as well. And the goal eventually is to sort of start packing a whole bunch of the unique technology that we have inside of this platform so that anything you want to do, you can do anywhere. So that's kind of a quick overview, a little bit of a sneak peek of the next sort of product that we have on the go. And yeah, maybe we have a bit of time now. So, and we both covered quite a lot of material very quickly. So I'm guessing there might be some questions. So maybe we'll just open it up for questions at this point. Anyone? Jean-Claude?
What about the simulation times? Like the speed? How much can you multi-thread or just run the simulation onto multiple processors? You can speed it up?
So we end up running, you can run different, like if things aren't dependent on one another, you could run those on separate processors. And in the old days, like before Ziva, when we were involved in sort of writing similar solutions inside of studios, we would, the actual machines were a lot slower back then, so we would split things up a lot. Like, you'd sort of have like this part of the body and that part of the body, and then that would solve, and you can combine it, and then you'd do the fat or whatever. But nowadays, like the solves actually, the Ziva solver is a lot faster than what we did before, and computers are a lot faster. So we tend to try to run as much of it together as we can, but it is a dynamic process, so you are kind of limited by the fact that it has to run sequentially. Like you can't split it like you would a render, at least unless you choose to run it quasi-statically. So if you're not going to solve for dynamics, but you just want to solve for shape, you could split that. Yes?
I mean, you were
Yep.
approaches, and you want to have parts of them just being deformed. You have also approaches towards having like a simplified deformed solution, or basically taking simulation effects back into into a blend shape setup that can be driven by the former deformation results based on like I don't know, calisthenics that you feed into
Yeah,
it.
yeah, absolutely. So so we have like in the software that's currently available to you right now. If you do want to run dynamics, you're not limited to doing a full anatomical setup. You could do something much simpler if you just want to add jiggle to something. Like we have a goaling attachment, which allows you to sort of goal your simulation to a traditional rig, if that's what you have. And then you can just get the oscillations that you'd expect from the dynamics. If you want to bake it down to something which you can interact with, today, as far as commercial productization goes, I would probably use the quasi-static solver, or either that or run it in dynamic mode with your frame rate at like 1 frame a second or something like that, so that the dynamics settle, and then you could bake those out as shapes and then add them in as blend shapes into a traditional rig. The real-time solution that we have, which isn't productized yet though, is kind of what you're describing. So you feed it a whole bunch of bakes, and it runs the machine learning stuff on it in order to correlate. Yeah.
As well, if you're looking into that.
Yeah, we've
Something very promising.
yeah, we've demonstrated it kind of behind closed doors 3 years ago, and we've been iterating on it to make it really friendly, because it's the parameters that you're setting are pretty high dimensional, so we're trying to simplify the process so that anyone can do it without having to really have a deep understanding of what it's doing. So yeah.
When will the version of that be publicly available? Or how far are you?
We do have people testing it right now. I can't give you a specific ship date yet, but we'd like to get it out as soon as possible. But yeah, but for us, it's important that you only get one opportunity to make a first impression, so we want it to be good before we get it out the door. So yeah.
How do you switch the?
Back to the deformance, so you would basically say that as soon as you would say, okay, we're going to simulate everything, then you're more set back to that traditional rigging approach for deforming everything itself, right? There's nothing out of the box for this one right now. Or like a standard muscle deformation for like tube-like muscle.
Yeah, no, this is we have more in common with a fluid solver than we do with a muscle, like a traditional muscle thing. Yeah. Yeah, no, for sure.
And just to your other point at the very start, I think you mentioned that you don't necessarily need a full anatomy in a character. So this is one that's just one single tissue. It's using something called the body bone approach, where there's a slimmer version of this guy inside here, and everything between here and the outside is just tissue. So you get some pretty cool effects. Like the hand is interacting with the belly and pushing it round, and you get these kind of nice volume conserving effects, and the jiggle obviously and stuff. So
Yeah.
you don't necessarily need an anatomy in there.
Yeah, and that is like that commercial that Fable FX did with the polar bear and stuff. That it was this sort of approach that was employed.
Yeah.
Yeah.
Yeah. Or it could be a couch.
Could be a couch.
Where's the Ziva couch?
Yeah, I guess that is the other thing. Like, so we're really interested in characters, but ultimately it is a general purpose elastic solid simulator. So you can simulate anything that is elastic in behavior. So like foam rubber cushions, for example.
Yeah. The cool thing with our solver is that because it's using real-world physics, you can look up things like the Poisson's ratio on Wikipedia of different materials, like tissue or bone or wood or foam, and you can plug them into our solver, and it should give you the right result because it's using real-world engineering stuff. So it's kind of a nice thing to bear in mind. So this one is, these bowling balls are also tissues. They're very stiff, obviously, and I've just cranked the density up on them. So you can represent quite a wide range of different materialities. It's pretty cool. This was a cheetah that we did the warp to. So we took the lion that we have and we warped over to the cheetah. Got some pretty cool results.
And then I'll just load this plugin, one sec.
And that came from This is a horse that I'm working on at the moment. It has some obvious flaws, which will be obvious to you as well. But we had a local company actually mocap a horse, which is cool. And then we built out its anatomy and things. So there's the skin's tearing a bit here, and that's a collision issue, but everywhere else has kind of got a pretty good start, I think. So, it feels heavy. There's a nice sort of weight to the muscles, a nice jiggle. It's pretty ripped, and I always think with this stuff, it's better to start in a place where it's too ripped, too jiggly, too slidey, and then dial it back rather than the other way around, because, yeah.
So if there aren't questions, maybe we'll just cover a couple things which we kind of whipped past in the demo to give a little bit more detail on some things.
Yeah. Switch back?
Sure, if we could switch back to this one. So a couple of things that, so I'm just going to, do boring sphere demo. This isn't as exciting as seeing real things, but it's really quick and easy to iterate with. So I'm just going to turn this into a bone. I'll turn that into a tissue. I'm going to scale down the solver. So one thing that is neat with this too is that if the material properties of the tissues by default, it matches real-world muscle. And like in the case, say you're working on a giant creature, like I don't know, like Godzilla or something like that, and people are used to sort of seeing human scale physical effects on creatures. So if you're to make the material properties like a real creature that size would be, like the stiffness of his muscles would be like I-beams, like it would be ridiculously stiff. But so you can actually tune it at human scale, and then you can adjust the size of your solver in order to affect the overall oscillations of the material. So it makes it easier to sort of adjust things like that. We've done a lot of work to try to make the solver as production friendly as possible as well. Like we know about the challenges about getting your character from the space that you build it out to your shot space, being able to deal with situations where for effect things might accelerate way unrealistic velocities. We have this feature in there called inertial damping that helps remove momentum from the system. But yeah, so I have these two objects here. I'll just attach them together. And make an attachment there. And I'll give myself more frames to play with as well. So if you look now, if I interactively play it back, you'll see it's at a certain frequency of, you can tell how big it is based upon how it's oscillating and the stiffness of it. If I change the scale of the solver, so I'll go to 1 now, and then if I were to do this, same thing. So the stiffness is the same, but as far as the tissue is concerned, it's now 10 times bigger than it was before. So it's not, the material's not strong enough to fight gravity. So that's what that represents. So it's a neat way to sort of quickly adjust things. Some of the other stuff that you can do, which is kind of cool, is, and this was something which got practically used on the Meg quite a lot. So there were a lot of shots that needed to be framed. The director wanted to frame it to camera a certain way, so they were scaling the shark per shot in a lot of cases. And if those of you who have used physical simulations to do this sort of stuff, that can be a challenging situation in the best of times. But because of how we end up solving things relative to that world frame, you could do stuff like this, where I'll just scale it up or down or do whatever, and then then you can move it away from the frame after that's happened, or move it with the frame and it doesn't see that it's moving. I'll just demonstrate the inertial damping quick too. So per element, or per tissue, you do have this attribute on it called inertial damping, which is right there. When it's set to 0, the tissue receives the full momentum of the system. If you set it to 1, the affine modes of deformation, so like the ones that, like the things that really kind of just relate to the position, the rotation, the shear of the object, those end up getting solved quasi-statically. But all the higher frequency stuff is still fully dynamic. So what's cool with that is the object could whip around at whatever speed you want. It's not going to get any momentum. But if you whack it into something, you'll see wave propagation because it hits it. So I'll just sort of show I don't have anything to whack it against right now, but if just solve it. You'll see it's there. I'm moving it. It doesn't see any momentum. But if I do rotate this, gravity still has an effect on it. One of the other features around, Andy kind of showed the overall TET size that you can adjust interactively. A lot of times you'll have situations where you just want more TET resolution in one part of the mesh, but not in others. So we have added, like he touched on, most everything has paintable attributes. So with the TET mesh, you can go in here and just paint where you want smaller TETs. And if you want to adjust it, there's a surface refinement number here, which you can kind of think of almost like a subdivision level. And then if I put that to a higher number, the TETs get smaller just in that area. So that's a nice way to sort of control, help balance the speed versus the frequency that you want. And also, actually, one other thing, in case it wasn't clear earlier, the resolution of the TET mesh really just has to be the right resolution to contain the deformation and the oscillations that you want. So a lot of times you can get away with really coarse TET meshes for things like muscles because they just squish and bulge. You don't normally see waves run up and down muscles unless you're doing high-speed photography. So you can get away with coarse TET meshing. All of the collisions, attachments, all those forces are applied at the surface that's embedded and get propagated out to the TET mesh. So you don't need to, you can decouple the concept of the resolution from how things are set. Maybe I'll just see if there's any other questions. We're almost out of time, or we are out of time probably, but any other questions?
Cool.
No? Great. Okay, thank you very much.
Thanks, guys.